Hello, beautiful humans. Today we're going to talk about inverse functions and how we can find them in a variety of different, depending on what we're given, right? So an inverse function is basically a function that undoes another function. So if we plugged in a input to one function and get some output, if we were to plug that output into the inverse, we would get the input that we got from the other function. So undo each other. If we look at a graph, inverse functions will be a reflection of one another over the line y equals x. So in this example here, this is the line, this is the line y equals x. Okay, so that's a line with a slope of 1 and a y-intercept of 0. And you'll notice that this function f of x is a reflection, or this new function over here, f to the negative 1 of x, is a reflection over that line. Same thing over here. Our f of x function is in blue, and our f to the negative 1, which is how we identify an inverse function, is in green. And again, it's a reflection over the line y equals x. And it's always going to be a reflection over the line y equals x. From a table, again, what's happening here is the inputs and outputs are switching. So if you have a table of values, your x values in your original function are going to become your y values in your inverse function. So if you're given a table, we're really just swapping our x and y values to find the inverse table. All right, algebraically, we do this a little differently. So what I just said in a variety of different ways is that the x and y values swap. So to solve these algebraically, we're literally just going to swap the x and y values and then resolve it for y, because that's typically how we write functions as like f of x, right? So f of x is y in its fancy function close. So we're going to replace that real quick with just y equals 3x minus 7. And then we're going to swap our x and y. We're literally just going to replace their locations. So we're going to call this x equals 3y minus 7. Again, an inverse is swapping of x and y. Swapping of those domain and range are switching, right? And so then we're just going to resolve this for y so that we can write it as f to the negative 1 of x, which is how we indicate inverse functions. So we're going to add 7 to both sides. Again, just inverse operations here, equals 3y, and then we're going to divide by 3, f to the negative 1 of x, again indicating that we have now found an inverse. This is notation for an inverse function, is going to equal x plus 7 over 3, which you could change the way that format is written if you wanted, but that is the inverse function of the linear function 3x minus 7. If you were to go ahead and graph both of those linear functions, you notice they are a reflection of each other over the line y equals x. If you were to plug in x and y values to create a table, you'd notice that the inputs and outputs switch for those. So that's what we're doing here. All right, so in this first step, we're just given a table and we're supposed to create an inverse table. So if this is for f of x, we want to create a table for f to the negative 1 of x, the inverse function. Okay, this is as easy as you might predict. We're simply going to rewrite all our y values on the x side and pair them up with the x values that they correspond to. Again, just swapping our x and y values because that's what an inverse is. The inputs and outputs switch. X and y being inputs and outputs, right? Okay, so if this is f of x, you're going to try this one. I bet you got this. F to the negative 1 of x is just a simple flip. Oops. Make sure you're pairing up your numbers there. 13 goes with 4. Here we go. All right, pretty easy from a table. All right, now we're given graphs and we're determining if they are inverses of each other. So what we really need to pay attention to here is that inverses, the inputs and outputs switch. So you could absolutely write down table values and see if those inputs and outputs are switching. You can also draw your line y equals x, right? And that's not perfect, but you get the general idea, and see if these appear to be a reflection. Okay, so notice on the line, they share that point right there, which makes sense. And then do these each appear to be a reflection over this line? Yeah, it's looking pretty good as this one goes out, that one goes out, right? So this appears to be a yes. This is, these appear to be inverses of each other. On my next example down here, again, I'm going to go ahead and draw my line. A little bit trickier on this one, but I can, there. Okay, again, this looks pretty good. Looks to be a reflection potentially, right? Appearing to be equidistant here from each of those points. Again, you could also check points. So if we wanted to check, like this is the point 0, 3. So we have the point 0, 3 written in dashed lines, kind of fun. Okay, and then we have the point 3, 0. Oh, look at that. Again, the inputs and outputs are swapping. So you can absolutely check points on these. You can also check for that reflection line. So let's look at the you try example. Again, when I draw my line here, this is looking like it's probably a reflection. Keep in mind, the bottom half of this parabola, if we were to solve algebraically, would not appear because it would be a square root function, right? The inverse of a square function, a quadratic function, is going to be a square root function. So when you introduce that square root, remember you need to introduce that plus or minus. That's how we're going to get the bottom half of that quadratic out of our inverse. But yes, again, this appears to be a reflection. These appear to be inverse functions. Okay, over here, again, I'm going to draw in my line of reflection. This is not looking good, right? So these definitely don't appear to be a reflection over this line. I'm just going to check a point and make sure I'm not missing something here. This is the point 0, 6. So if I have the point 0, 6 on my blue function, I should also have the point 6, 0 on my red function. When I go over to 6, 0, though, I do not have a point on my red function, so these are not inverses. So this would be a no. All right. So how do we do this if we're just given the graph? How do we draw the inverse? Well, if you're really good with reflection, you can draw your line of reflection and do your reflection points. If that's not so much your jam, I would probably just create a couple points, table for myself, and then flip them and regraph it. Okay, so this point here looks like 4, -7. Okay, so there's one ordered pair, kind of an important one, right? And then I want to get a couple points to represent both sides of my quadratic. So I'm just looking for nice whole numbers here. This appears to be not stretched. So I notice that I have the point 5, -6, and the point, what do we say, the vertex is at 4, so this is 3, -6. Okay, so when I flip each of those, my inverse, we'll do in blue, is going to be -7. Oh, that's not very much different. Let's try a different color. Let's try purple. Okay, so my inverse function is going to be -7, 4, and then -6, 5, and also the value -6, 3. And then I'm just going to plot those points, and knowing what I know about how quadratic is shaped, I should be able to draw the rest of my function. Okay, so -7 up 4. Okay, and then -6 up 5. And then we're going to have that one as well. And then my quadratic is going to be shaped like this. Again, if I were to draw in my y equals x line, I should see that these are a reflection of one another. Again, we have that point matching up, and we should see each of those points balancing each other out, the inverse. Okay, so go ahead and draw those out. Give this one an attempt with this cubic function. Okay, so again, I would start by identifying points. I'm going to start with the locator point. Locator point here is at -4, 0. Okay, and then we have over 1, up 1. Okay, so this would be -3, 1. And then we also have left 1, down 1, right? So -5, -1. Hey, boys. And then, excuse my dog's barking in the background. It's fairly early and they've got their morning energy to get out. Okay, so now we are going to write our inverse. Remember, we're just going to flip these points, right? So we have the point 0, -4. We have the point 1, -3. And we have the point -1, -5. I'm just going to go ahead and plot those again. Use what I know about how this cubic function is shaped, and the inverse, guys, is going to look like a cube root function, right? Think about how we solve these algebraically. If you have a cube and you want to undo it, you're going to take a cube root. So these, hopefully you're starting to see some patterns in these, the way these functions work and are shaped and look. Okay, so 0, -4, that's an important point, over 1 down 3, and then -1 down to -5. Okay, so remember, this has been reflected, okay? So it's now our sideways. So this thing's gonna go something like that. Again, that's not a perfect drawing. You could definitely get more points to see this more clearly. But again, if you check out the general idea here, this appears to be a fairly accurate reflection over that line. Again, that line's not perfectly straight or through the origin, but you get the general idea just from graphing a few points that these are in fact reflections of each other. All right, so most common way that we're going to do this going forward is going to be algebraically. So what we're going to do, again, is just like in that vocabulary section, we're going to swap our x and y values, and then we're just going to go ahead and resolve for y, and we're going to relabel it as f to -1 of x, indicating that we did, in fact, find an inverse. So again, we're going to start just by calling this y equals -2/3 x plus 7. Then we're going to swap our x and y terms. We're literally just replacing x with y and vice versa. So now we have x equals -2/3 y plus 7. Again, an inverse is just swapping of the inputs and outputs. So that's what we just did. Technically, we now have an inverse, but it's not in inverse notation. So we need to reorder these things. We're going to subtract 7 on both sides. X minus 7 equals -2/3 times y. Then we're going to multiply by the inverse. We're going to multiply by -3/2 to cancel that 2/3 out on both sides. So over here, we're going to multiply by -3/2. A couple different ways you could write that. If you wanted to keep it in slope-intercept form, you could do -3/2 x minus 21/2, right? Or plus rather 21/2. You could simplify that further if you wanted, equals y. But again, we really want to replace this y. The whole point of reordering all of this after this first initial step here, where technically we found the inverse, right? The whole next several steps were to rewrite this in function notation. So make sure we actually replace that with f to the -1 of x. Again, that -1 indicating that this is an inverse function. Okay, so this would be our answer here. Again, we're going to replace that y with f to the -1 of x. Super important. You will lose points for that. If we were in class doing tests on paper, etc., it is really important that you use that inverse notation. All right, give this one a shot. So again, we start by just rewriting our f of x as y, because it's f of x is y dressed up in its fancy function clothes. Then we're going to swap our x and y. Again, technically right here at this step, you have found an inverse. The rest of this process is simply getting it into the correct form. So now we just need to go ahead and resolve for y to get y by itself, and we're going to replace that y with f to the -1 of x. We're going to add 9 to both sides. Okay, so remember what I said about that. When we undo a square, we take the square root of both sides, right? So technically, when I introduce the square root, we now have plus or minus the square root of x plus 9, okay? So that becomes important because otherwise we're just going to have that, the positive part of that square root function. And technically, the inverse is the entire thing. So now we have plus or minus the square root of x plus 9 equals y minus 4. Now I need to add 4 to both sides. So what we end up with is 4 plus or minus the square root of x plus 9 equals what? F to the -1 of x. Again, kind of ugly the way that's written, but that's the inverse. And if you were to go ahead and graph that in Desmos, you'd see that you'd get the top part of the curve and the bottom part of the curve because we have that plus and minus in there. You'd want to graph those separately, by the way. If you do try that in Desmos, graph one that is 4 plus the square root of x plus 9, and graph the other one that is 4 minus the square root of x plus 9. Okay, all right. We need to undo this one. So again, start by replacing x and y. In fact, if you want to get fancy now that you get the general idea, we're already just going to replace, right? So we're going to say 3y minus 4 cubed over 7. Okay, step one, we want to multiply by 7, get it to the other side. So now we have 7x equals 3y minus 4, and we are going to have to undo this cube with a cube root. Again, think about how these functions look like a reflection over that line y equals x when we think about these functions we've looked at before, cubic functions and cube root functions, particularly when we look at the mother functions. Pretty easy to see that they are in fact a reflection of each other over that line y equals x. Okay, so now on the left we have the cube root of 7x is going to equal 13y minus 4. Again, I don't need plus or minus here because cube roots will produce negatives or positives depending on the input. So no need for plus or minus here. Add 4 to both sides. So now we have 4 plus the cube root of 7x. By the way, you could also write the cube root of 7x plus 4. Same, right? Order doesn't matter with addition. Equals 13y. Now we need to divide by 13 on both sides. And we have 4 plus the cube root of 7x all over 13 equals what? F to the negative 1 of x, because that is the inverse. Again, I'd encourage you to play as you're processing this information. Go ahead and graph these in Desmos and just further enforce that reflection idea. All right, last one you try, and let's see what you get here. So again, I'm going to replace my x and my y. I'm just going to switch my x and my y right away, and then I'm going to start moving everything away from that y so I can have it in the correct notation. Okay, to undo this 3/5, I'm going to multiply both sides. Oh, come on. I'm going to multiply both sides by 5 over 3. Again, depending on how you prefer to write this out, we could do 5x plus 40 all over 3. Again, how you simplify this isn't really a huge deal to me. I care more about this process of inverses and making sure you understand how to manipulate equations. So take the square root of both sides, square root of both sides. Okay, here I do want to point out first we need this plus or minus, and also you are not allowed to have a square root in the denominator. So as soon as you have that square root of 3 in the denominator, that is not allowed. We cannot have a square root in the denominator. In order to undo that, okay, so what we have, really we have the square root of 5x plus 40 over the square root of 3, and we're not allowed to have the square root of 3. So we'd multiply by the square root of 3 in the numerator and the denominator. Remember, the square root of 3 divided by the square root of 3 is just 1. You can multiply anything by 1 as you see fit. So when we multiply, this is like 3 being multiplied by everything inside that square root on the left. So what we end up with is 15x plus 120 all under the square root, all over just plain old 3, no longer the square root of 3, because the square root of 3 times the square root of 3 would be the square root of 9, which is just plain old 3. And now over here, oh, and don't forget that plus or minus. And over here on the right, we now have what? X to the negative 1 of x function notation. All right, hopefully this makes sense. Again, the basic concept here is just our x and our y values are being swapped. Inputs and outputs switch, domain and range will be opposites, and that's the basics of inverse functions. Have a wonderful rest of your day.